Anyway, thanks for coming to the LTO. We hope you enjoy and learn a lot from the program tonight. It's really a pretty small world. About 6-8 months ago, I had the pleasure of attending a program. I'm in an aviation group here in the Denver area, and our speaker that night was Lieutenant Commander Paul Hemmeck, who was talking about the NOAA Corps. And I thought, well, what is that? I don't know. Sounds cool. And I went there and I was amazed that there is a branch of the military whose purpose is to support NOAA in their ships, fly their aircraft, manage research projects, and conduct diving operations, and that also that Paul was based at the Space Weather Prediction Center in Boulder. And so after the meeting, I cornered him and I said, Space Weather Prediction Center. My wife and I volunteer at an observatory in Berthoud. Is there any chance that you'd be willing to talk about space weather to us sometime? And I said, and if you'd be willing to come up there, I said, you know, we try and get the young people interested in math and science through astronomy, but you're talking about a career opportunity in serving our country and studying the environment, supporting NOAA's missions. And it just came together. And Paul mentioned that one of his colleagues, Shawn Dahl, lived here in Berthoud and had actually just spoken with a couple of high school classes on the geophysics science classes in talks that he gave on space weather here, and that Shawn lives here in Berthoud. And so we're lucky enough to have both of them here. Paul's background is that he started as a junior officer aboard a NOAA ship, and then after going through a couple of service levels, he gained acceptance into flight school, and then was based at the National Operational Hydrologic Remote Sensing Center in Minneapolis, Minnesota as a low-level snow survey pilot.
There'll be a quiz on that.
Well, I grew up in Minneapolis, and I was a paper carrier when I was a teenager, so I did snow surveys also, but I think at a lower level. So we got to talk Minnesotan and stuff like that, and it was like, oh, we so got to get you here, don't you know? And so Shawn spent 22 years with the Air Force as an intelligence analyst, meteorologist, and space weather forecaster. In 2015, he was hired by this Space Weather Prediction Center. Based on his backgrounds, his interest in space or experience in space weather particularly was 4 years in Puerto Rico at an Air Force Solar Observatory, 2 years as a space weather forecaster in California, supporting the Air Force and creating specialized space weather forecasts. And
those are all places with nice beaches.
Isn't that a shame?
And as I mentioned, Shawn does live in Berthoud. He did present talks on space weather to the Berthoud High School 9th and 10th grade geophysical science class, but I negotiated with him that the material that he covers tonight will not be on the final exam. Please welcome Paul Hemmeck and Shawn Dahl from NOAA.
Thank you, Glenn. Thanks everybody for inviting me out here tonight. It's great. I know Commander Hemmeck appreciates it as well. I love space weather. When I came in the Air Force well over 22 years ago, I was in the Air Force for 22 years and have been working as a civilian between the Department of Defense and the National Weather Service for going on 9 years now. So I've had a pretty good amount of time on the space weather side, and since astronomy is a hobby of mine, when I went from meteorology, which was what I did after intelligence, I did meteorology, so I'm a meteorologist too. Once I got into the space weather side, since astronomy was a hobby of mine, I was like, I have got to do this for a living when I get the chance. It took a while, but I finally made it, so now I'm happy as a lark over at the Space Weather Prediction Center, where I've been for just only a year now, because I came from a place with beaches in Hawaii before I came here. 2.5 years over there. So enough about me. You heard a lot of that. If you have any questions later on, I'll be around for a while, and I'll be happy to answer what I can for you. So let's get right into it. Space weather. Who would have figured? You normally think of space, think of alien movies, and nobody can hear you scream that nothing's going on out there. It's just a vacuumless void. Well, generally, yeah. But there are things that are going on in space that originate from that fabulous star that gives us life here, the sun. From there, all the way through the space medium to planet Earth and beyond, that the sun controls and affects us here, right here on our planet, and around our planet, which in the space age is extremely important. If you can take a mental note, because I really don't want to backtrack on the slides, I want you to focus on this for a minute, for those of you that can see that. And if you can't, I'll describe it later on, and maybe some of that will make sense to you. So let's jump into it. Space weather. Well, let me tell you 2 stories. In December of 1972, for a week, about the 2nd week of December, the Apollo 17 lunar landing mission was in place. The astronauts spent 3 days on the moon. Over 21 hours of those 3 days, they spent in something called extravehicular activity, EVA for short, because I'll use that word off and on. So Eugene Cernan and Harrison Schmitt were the astronauts. They were on the moon, and by a stroke of great luck, Harrison Schmitt was a geologist. He wasn't a test pilot type that had been bred into the astronaut side. It was a geologist sent to the moon. This was a really geologic-specific mission. But they spent a lot of time on the lunar surface, driving around in their lunar rover, doing geologic surveying, collecting samples, grabbing rocks, doing experiments. But what they didn't know is that there were things that could possibly happen in space that we weren't really prepared for yet. In April of 1972, Apollo 16 had been to the moon. So if you take April and December of 1972 and you bring them to the middle in between, that happens to be August. So in between those 2 lunar missions, both of which spent 3 days on the moon, astronauts were out there. On 4 August 1972, one of the largest radiation storms that ever recorded from the sun occurred. And what I mean by a radiation storm is that a bunch of atomic particles that aren't normally in space, and those of you that know atoms, we're talking mainly about protons. And when I talk about protons, I want you to envision an elephant. Okay? If you have one elephant and another elephant, but the one elephant is 2,000 times more massive than the other elephant, that's what a proton is in the atomic world compared to like an electron. A proton is 2,000 times more massive than its electron. That radiation storm was a bunch of energetic protons going through space, and if that had happened and the astronauts were on the moon on that date at that time, they would have received what many scientists believe today would have been lethal doses of radiation. Remember, the moon has no atmosphere. Fortunately for us, we have an atmosphere. So there already is a very important thing. Normally, space has less than 1 energetic proton going through a very small parcel that we measure. This storm produced thousands of them a second. So you can imagine the amount of radiation that astronauts could have received if, by some unfortunate stroke of luck, we had been to the moon on 4 August 1972. So right away, space weather is a very important thing to know and think about when it comes to NASA, astronauts, people that fly up high in the atmosphere, as well as satellites and other things that we'll get into later. Here's a what did scenario. Another reason space weather is extremely important. On 10 March 1989, an enormous burst of solar energy happened from the sun. This one wasn't necessarily associated with a gigantic radiation storm, but this one spewed out into space a massive quantity of what had been solar atmosphere, literally, blasted off into space at millions of miles an hour, treading on towards planet Earth. On March 13th, 1989, there were some power plant operators that work with the electricity and the power flow of what we call the power grid up in Quebec, Canada. They were sitting there in the middle of the night about 2:15 in the morning, and unbeknownst to them, Earth was now getting bombarded by that large cloud of energy that had been released from the sun. It took a while for that to get here, but it finally arrived. What had happened is it was so strong when it hit the Earth, it started inducing electrical currents that don't belong there. And when electricity flows, it tries to fly things to flow through. It can be pipelines, it can be power lines, telephone lines. And what happened that morning, unknown to them, is all this extra power started forming and flowing along their power grid. Half an hour later, about 2:44 in the morning, these power plant operators, one of their capacitors went down. Suddenly they were starting to lose the ability to control electricity. Less than a minute later, more went down. By 2:45 in the morning up in Quebec, Canada, Hydro-Quebec Electric Power Company lost power. Boom. That power controlled millions of people in and around the Great Lakes region in Canada. By a stroke of luck, New York's power company was struggling to maintain power as well, but they were able to divert power to extra capacitors and somehow avoided a complete blackout. But this image right here, there should be lights in and around the Great Lakes. They lost power for all that. This black area up here illustrates the area that was lost of power on 13 March 1989. Now think about that month, March. That's coming out of winter going into spring. It's Canada. It's cold. It was a cold night. The temperature was about 19 degrees Fahrenheit. People woke up in the morning, were shivering. The house wasn't heated anymore. They had no power. They couldn't turn on the TV to see what was going on. There was no morning paper because the presses stopped running from electricity loss. Some people's water wouldn't work because electricity controls the ability to flow a lot of water in some cases. Refrigeration stopped. Life kind of came to a standstill. The subway systems and things stopped running. It really created an economic impact. That power was not mostly restored until about noon that day. So for almost 12 hours, a lot of people were without power. And when I say they lost power, they lost power. If you can see that image down there, that's a burnt out capacitor or transformer piece of equipment. That's what happened to a lot of that equipment. So much electricity danced around those just didn't shut down, they burnt out. You can't replace those things on a whim. They're extremely heavy. A lot of times they don't even have them in production. They have to build them. So, if that had happened in the United States, this is an image unrelated to the sun, but from a power outage that happened around the New York back in August of 2003 for a totally different reason. But look at that. It looks like somebody took a bite out of the United States. Imagine that stretching all the way up here into Canada. That's potentially what could have happened in 1989. And that is today what the Federal Emergency Management Administration, FEMA, is one of their worst nightmares. And that's why we get in touch with them when we're expecting a possible extreme geomagnetic storm. So imagine what the press would do. If something like that happened today, if little town of Berthoud, Colorado loses power, that's not going to make national news. What do you think would happen if New York City and everybody surrounding that area lost power? Is that going to make national news? Yes. Is that going to make world news? Yes. So in today's social media venue, we're able to get a lot of information out there, and the press picks up on things. And today, the press really likes to highlight interesting things to get your attention. So when things are going on in the sun, or things are happening near Earth that are effects from the sun, the press will often talk about it. But don't let that scare you, because they like to glamorize things. I mean, think about it. Big solar storm hitting Earth. That's going to cause you to perk up your ears and say, whoa, what's going on? Strong solar storm heading to Earth. Unleashes major solar flare at Earth. It's kind of terrifying stuff, don't you think? So if you ever hear about this stuff in the social media or the press, please take a pause, say, hey, something's going on. Let me go to the Space Weather Prediction Center website to see what's really going on. Because oftentimes it's not as serious as it might be advocated in the press. So just kind of keep that in mind. But there will be a time where it will be serious. So you've heard about some of the impacts. Radiation storms you heard me talk about. You heard me talk about geomagnetic storming causing power outages around the Earth. Other things happen. Satellites get affected by space weather because some of these high energy particles actually get into the platform and can cause erroneous commands to happen. It can shut power off. It can cause commands that don't belong. And satellites can be lost control of, so to speak. because of things like this. Communications for ham radio operator types in particular, or airline pilots. Communication is extremely important, right? When you have a major event from the sun, depending on what took place, it'll often black out the radio spectrum, especially in the HF realm. Aircraft operations rely on that, especially when they're flying over the poles. Who do you think else besides astronauts might be concerned about radiation storms from the sun? Airline companies, especially now that they're flying over the pole, the North Pole, to save money on fuel. It's a shortcut. They can't fly over the polar regions anymore when there's going to be a potential radio blackout, because HF radio is really their only good backup means or primary means of communicating when they're out there with nothing around. They're concerned about radiation. They're up high, we're down safe on the ground. They're up high, and especially around the polar areas, they're not as well protected. So when radiation storms are possible, they're going to stop that flight as well. So they're very interested. You already heard about power grid and what that can do, and that should be immediate concern to all of us. GPS, very relied on these days. Accuracy becomes a problem more than communication with it. Delays, which is what measures GPS and where you're at, all very timing essential. Just being off a few feet. Who's seeing the things on TV these days about cars that are going to drive themselves? Okay, that's relying on GPS. If GPS is not going to be accurate by a foot, you're going to want to be on the road with these driverless cars? I'm not going to want to be on that road. That is going to become even more of a concern now. We're not talking about just getting to the bar or to the school. We're talking about potential danger. So what does this all mean? Well, as mentioned, the Space Weather Prediction Center is the United States' focus on these things. It's to help you, the public, know what's going on and what and how it might affect you, what it means to your life. We fall under the National Weather Service, which falls under the National Oceanic and Atmospheric Administration, NOAA for short, which falls under the Department of Commerce and thus the government. Just note the symbol. You know, we're a peaceful organization. That's what the Weather Service is. That's what NOAA is. If you've never really looked at it or thought about it, it's the ocean, it's a seagull, and it's the sky. A peaceful symbol. That's what NOAA is, and I'm pleased to be part of that organization. So to communicate what's going on to the public with space weather, we focus on three primary things. Now there's a lot of things we look at, but our focus for what it means to you is normally on three major things. It's giant bursts of energy from the sun, we term as solar flares, and what that means to communication in particular. Radiation storms we've already talked about with astronauts, airline industry, that also affects communication. A solar flare, when that happens, the effect is immediate here on Earth. It already is. If you think about it, the speed of light, when we see the sun, we're seeing it as it was like 8 to 9 minutes ago. So when a solar flare happens on the sun, we're seeing it as it was 8 minutes ago. So it's here. The effect is already here. When we notice it happening, it's already having an effect. So it's already heated up our atmosphere and it's causing radio blackout problems. Radiation storms, these energetic particles are going at near relativistic speeds. That means almost the speed of light, but they're a little slower. So they can get here within 15 to 30 minutes in a really strong event, or it can take 24 hours or more for them to get here, depending on what their path of travel is. So we actually have maybe a little warning time here. We have no warning time here with solar flares. They happen, the effect is here, all we can do is alert on it. Radiation storms, we might be able to get a little bit of a warning out there, but there's no way we can do a watch. When it comes to geomagnetic storms, that's this giant blast of magnetic cloud, so to speak, that's traveling slower through space, and it takes a lot longer to get here. The fastest known one to have gotten here is about 18 hours. That's extremely fast. Usually it takes around 3 days. So not only do we have the ability to alert when it's happening, we have the ability to warn well in advance normally, and we have the ability to put out a watch to let people know, hey, this may happen in 1 or 2 or 3 days. So that's kind of where we're at with our technology. Unlike the mainstream weather service and their terrestrial weather, they've come up with all sorts of great things, radars and satellite imaging tools and supercomputer models that really help them to iron this stuff down, and they're getting pretty good at their warnings. We're still in our kindergarten days when it comes to space weather. So let's jump back in a little bit of history briefly, just so I can Kind of illustrates how some things work and what we're focused on today. So Galileo Galilei in the 1600s was one of the first scientists from way back that started looking at the sun and kind of documenting what he was seeing. Sunspots had been observed for years prior to that, but he was the first one that really started taking note and studying it. And he noticed that these sunspots traveled from day to day across the sun. He didn't know what that meant. He had no idea what a sunspot was, but he took note, and thank goodness he had some really good journals that he was keeping and scientific notes. So what he basically discovered is that sunspots move across the sun. Why do they move across the sun? Well, it took another guy in the 1800s by the name of Richard Carrington who discovered something called differential rotation. Okay, how often does it take for the Earth to make one full rotation? 24 hours, exactly right. We're a nice solid body and we have one solid motion, 24 hours. The sun is this massive ball of burning gases out there which kind of acts like a liquid. So it does not rotate at one set speed, believe it or not. The equator is actually rotating faster than the poles. So what happens is the equator takes about 25, 26 days to make a full rotation until it's back to where it started. The poles, it takes over 30 days. Imagine if that was planet Earth. If the equator was rotating in, say, 18 hours and the poles were rotating in 24 hours. What do you think would happen to planet Earth? Would we be able to survive? Would there be massive earthquakes and continents moving around like every day? That's what would be happening. It would wreak havoc on our little tiny planet, wouldn't it? Well, the sun is this giant ball. Unfortunately, it's not a solid body, so it doesn't rip itself to shreds, but it does make a lot of energy strain, and that energy has to eventually get released. So differential rotation becomes very important to how sunspots form and how they work around the sun. But another thing about Carrington is he happened to be sitting at his telescope one day. The day precisely was 1 September 1859. And what happened is he was making a sunspot drawing on a massive sunspot region that was on the sun. This thing was gigantic. You may not be able to make out the coordinates here, but essentially that thing, that big blob right there is at least, I don't know, 4 or 5 times the size of planet Earth. So here is this gigantic source sunspot. Well, he was drawing it and he happened to notice 2 areas of white light form around the sunspot. That's highly unusual. We don't usually see flares from the sun in white light. The sun itself is too bright. We don't see it at that spectrum. But he did. He made a note of it. He didn't know what it meant. Well, 18 hours later, some really strange things started happening around planet Earth. The aurora was suddenly seen all the way down to the Caribbean Sea. That's unbelievable. That does not happen. It does not go that far normally. So something unusual was happening. People in the northern sections of the South Pacific and the southern sections of the North Pacific saw northern lights. They didn't even know what they were seeing. We didn't have telephones. We didn't have radio. We had telegraph lines back then. People sitting and communicating by doing little ditty bops on one piece of metal to another that transmit themselves across the line. So we had telegraph lines. They started failing. They were sparking. Wood poles holding up lines, some of those burnt down. Fires started in some of the telegraph operating stations. Batteries were burning out. There was no commercial power. You couldn't plug the system in. You had batteries you hooked up to. They were getting overloaded. They were starting on fire. They didn't work. 2 guys, and it's a documented conversation, were talking back and forth using telegraph, by little dots and dits, and they were talking about their problems they were having. So they finally decided prudently to shut it down. They shut it down. It still worked. Imagine unplugging your TV from the wall and the thing's still working. You're going to be going from scratching your head to being spooked out, right? Imagine what these poor guys thought. There was so much extra electricity running along those telegraph lines that it kept power running. That's what happened in Canada. It got overloaded the system. It's not designed to handle that. So that is an extraordinary event. And we like to refer to that event as the Carrington event. So sometimes you might hear that term. We're talking about a really gigantic storm and an impact here at Earth. Quickly, these other guys. Schwab discovered there's a solar cycle. How many of you have heard of the solar cycle? 11-year cycle? Great. Basically, that's about the amount of time it takes for the sun to go from solar minimum back to solar minimum and solar max back to solar max, an 11-year cycle. We're coming out of solar max now and working towards solar minimum, and we'll be back to solar max down the line. Edward Maunder discovered that there's a sunspot cycle migration. Essentially, when a cycle starts, sunspots start forming in the higher latitudes of the sun. This dashed line is the equator of the sun, and then you have the southern latitudes and the northern latitudes. The sunspots start forming in the higher latitudes, and then as the years progress, they form more and more frequently towards the equator. And when you diagram this out, you see what looks like butterfly or moth wings. So we like to call this the butterfly diagram. Mr. Maunder and his wife spent hours upon hours, day after day, week after week, even year after year, looking through notes and records of sunspots, one taking turns, somebody scribing with a little pencil on a piece of paper all hunched over, and another one calling off dates and coordinates. And they did this time and again. So they actually discovered this. And there's actually a real original Maunder diagram in Boulder at one of the offices over there that they sent here to somebody they knew. So that's kind of a unique relic. So let's jump out of history and jump to today. Well, we've got all sorts of instruments in space. Thank goodness we're in the space age. Otherwise, we wouldn't be able to do half the things we're doing when it comes to space weather. I'm not going to go over each of these, but I will discuss briefly what some of these mean to you and their orbits. Essentially, there's different orbital points in space. So when we send satellites out there, we have to send them to a specific point because they're designed to do something and they need to be at that point. So you've all seen the weather people on TV. And if you see a picture of satellite imagery, which I know the guys here today are really interested in for the observing sessions afterwards to see what the clouds are doing, well, that's our GOES satellite. That's sitting out there miles away from Earth in an orbital spot that if this screen is the sun and you guys are all planet Earth, as Earth is moving, making its rotation 24 hours, that satellite is sitting right there with it. So let me try that again. If this is Earth, and I'm the satellite, I'm going with the rotation of the Earth. So every 24 hours, I'm making a complete turn as well. We call it a geostationary orbit, and that's where that satellite is. It needs to be in that spot so it can take pictures of moving clouds without being in different positions, otherwise it would never work. So that's why that's where it is. So not only is that monitoring meteorological information, we have a space weather package on there, and it's monitoring energetic particles, it's monitoring the magnetic field where it's at, it's monitoring X-ray flux from the sun. All very important data that we have to get at the Space Weather Prediction Center in order to do the things we're doing. Another one out there is ACE and SOHO. And I won't break down the acronyms for you, but there are detectors further out in space. They're about 1 million miles away, and they're at a point where if I'm the Earth and you guys are the sun, these satellites are sitting there all by their lonesome self 1 million miles away, and they are in a cycle of revolution with the Earth. So they stay in between the sun and the Earth as the Earth revolves around the sun every 365 days. So we always have something between us and the Earth to measure what's happening. So the ACE satellite sends us all sorts of data as well, and the SOHO sends us imagery, and particularly of the corona, so we can see what's happening out there, and that gives us a lot of heads up on what's going on. Other platforms are out there as well. The most interesting of these is this one for optical information. We are really beginning to rely on this platform to take pictures of the sun at different wavelengths to see what's going on. In stereo A and B, we're actually launched, believe it or not, to go around the sun. And the idea was to give us a three-dimensional image almost of what the sun was doing. Because believe it or not, when things happen from the sun, sometimes we don't know if it was on our side of the sun or on the far side when it comes to the stuff going on in the outer atmosphere of the sun. So these help us determine that. One of them just came back. They had both been behind the sun and we couldn't communicate with them. One, stereo A, actually has come up if this is the sun right here, it's just kind of come peeking out behind the sun over on this side, so there's Earth. So we're communicating with it. Stereo B is now over here, and we should be communicating with it, but we're not. We haven't been able to find it yet. We're going to launch a big effort here in March to try to find it again and communicate with it and make sure it's working. With any luck, we'll get it. If not, it may be just lost out there, lost in space. So we get all this data in. This is what I did in Puerto Rico. I studied the sun at this wavelength, which allowed me to look at a layer of the sun called the chromosphere. Did sunspot drawings every day and looked at the sun in white light, which shows up here as yellow, but essentially it's white light. For those that aren't familiar enough with the sun, there's 3 specific layers that we're really focused on in space weather. That's the photosphere, which is really kind of what we refer to the surfaces of the sun when we talk about a surface. It really doesn't have a surface, right? It's gas. But that's where the photons of light finally escape from the sun after millions and millions of years. And when they do, that's why it's called the photosphere, photons coming out. That's where we see sunspots. Above that is a little thin layer that transitions out to the corona. It's called the chromosphere. We study that at certain wavelengths, and we can see all sorts of things. You can see bright areas on the sun called active regions and plage. Darker areas, suspended stuff, we call those filaments. When they're on the side of the sun, we call those prominences. It's still essentially the same thing, and we'll get more into that later. And we get all this data coming in, fortunately, which allows us to do a lot of what we do. So here's how most people see the sun each day in the evening, right? Nice, tranquil, beautiful sun coming up every day, giving us life and warmth and light. Here's how we see it every day. This boiling cauldron of energy sitting out there that never goes away. It's always there. If you want a job where it's sunny every day, you walk into the office, there it is staring at you in the face every day. That's what we love, though. That's how we like to look at the sun. So let's get into a little more detail on what it means to you. Sunspots. Who's heard of sunspots? Fantastic. Sunspots, why are they there? What are they? Well, everything revolves around magnetism when it comes to the sun. The sun is a big, gigantic dynamo of energy there, and it makes magnetic fields because of that. A lot of these magnetic fields are exposed out into the far reaches of the corona of the sun. A lot of these are come up from more inside the sun. And when they kind of bubble up to the surface, so to speak, it causes problems on the photospheric surface of the sun. Imagine if you had a bunch of energy coming up from below and something begins to block it. Is that energy going to be able to go through it anymore, or is it going to have to go around it? It's going to have to go around it, right? Can't stop it. So sunspots are actually cooler areas. If the main temperature at the surface of the sun is around 4,500 degrees, these are actually cooler by 1,000 degrees or so. And then you got the warmer regions around it where it's bubbling up a little more, and so on. But these are focused. These are not just spots. They're actually wells, deep depressions into the sun. If you remember that image I was pointing out earlier, those that could see it, if you could fly over that somehow by a miracle, you'd see like you were looking down into a black hole almost. It's actually a depression in the sun. And it shows up dark because it's cooler. The area, this little structure going around, we call that the umbra. The area going around it we call the penumbra. That's a bunch of fibril areas of plasma and stuff that's trapped there that's coming in and going out of that well. We're not exactly sure how this works or how they form and why they are so symmetrical sometimes the way they are. But yeah, umbra, penumbra, sunspot region. It's basically an exposed area of magnetic energy, and we really focus on these and classify them and study them very detailed because it's really the only good way we have today, believe it or not, of determining the probability that there might be a flare on the sun and where that flare might come from. That is really the only way for us to tell that. So here's the sun. Told you it rotates roughly on average of every 27 days. That's pretty much the unit of measure we use when we're talking about something coming back. And you can see how these regions change. They rotate across the sun, they evolve, they dissipate, they go away, some increase in size. 109 Earths can roughly fit across the center diameter of the sun. That gives you an idea of scale on some of these regions. So we're not talking about small areas of magnetic energy. We're talking about gigantic areas of magnetic energy that become exposed. And so we study these, like I said, in great detail because we can then tell maybe the possibility that a region might flare. Here's a little more closer up. That was over at least 27 days. This is over just a few days. You can see how these change. You can see areas getting pulled together, pushed away, changes going on. There is a lot of dynamic stuff going on because of that differential rotation. And it's not just on the surface of the sun. The layers of the sun rotate at different speeds. Underneath is going at whatever speeds. So you have all this differential rotations going on. It's going to really do a lot to a magnetic flux area, isn't it? It's going to twist and turn and do all sorts of crazy things. Imagine a NASCAR or a race car driver as they go, I'll start the race at the same time, right? Eventually what happens? The faster cars start lapping the other cars. Well, that same kind of thing happens on the sun. That magnetic field starts to lap itself because one area is moving faster than the other. And when that happens, energy gets released, and we see it, so to speak, at the surface of the sun as sunspots. Magnetic energy. We look at the sun magnetically, believe it or not, to give us a flavor for how strong that sunspot region actually is. And what kind of dynamics are going on linearly. Is there a lot of moving? If you tried to follow like a front, you have high pressure and low pressure systems, right? It's usually separated by a front when a new air mass is coming in. Well, we try to do the same thing on the sun. We try to outline the areas between negative and positive polarities because it tells us how strong is that actually. Is there a chance that that field could rip apart and break and release energy? So we look at these very closely to get a flavor for that. And if you try to diagram where these magnetic field lines from negative to positive polarity go, it's almost impossible. This is just a mere tiny percentage of all the magnetic field lines that are connected in and around the sun. Some are very close and stay close to the surface that we just start to see. Some stretch well out into the corona. Some go, believe it or not, past planet Earth, way out into space, and before they come back. That's of a concern to us as well. We call those coronal holes. They're areas of open field lines, which means solar wind and things coming from the sun can get here faster, become more open.
Would it take a CME to shoot one out that far?
The solar wind continues well out into space. CMEs continue to travel as well, way out there, way beyond Earth. And NASA actually keeps track of these things, whether they're going away from us or not, because a lot of their spacecraft that are still out there exploring, like Saturn and stuff, they try to predict what impact that may have on the satellite and what's going on. So yeah, these are of concern, and they do travel well out into space. So solar flares, I've mentioned that word several times. You can read that. Great bursts of electromagnetic radiation. These are a major concern to us because they're our primary means of determining whether or not a radio blackout's happening on the sunlit side of the planet. For radio astronomers or people who monitor the sun radially, they're often associated with giant bursts of radio energy as well, and they can cause problems on radio spectrums, which is becoming of concern to airline operators as well, and radar operators, ham radio folks. All sorts of things can be concerned with radio bursts. But X-ray radiation is the main thing we're worried about when it comes from solar flares. Basically, what happens is field lines are sitting there, and when they break, imagine a rubber band. Who's played with rubber bands? How many of you have played with rubber bands, stretched it so far, eventually broke, and you painstakingly hurt your hand? That's exactly right. Okay, the same thing happens in the sun with solar flares and ejections. He's already jumped ahead, CMEs. What happens is these magnetic fields, they become twisted and contorted because of all this differential rotation and things going on. And they get stretched. Whatever happens with them dynamically causes stress. And when that stress finally gets to a breaking point, it snaps. A rubber band just doesn't snap and fall lamely to the ground, does it? It releases energy. You stretch that to a breaking point, and it snaps. It's got energy built up in there, and that slaps and hurts your hand, doesn't it? Or your friend. Hurts, don't it? Well, the same thing happens with the sun. We get all this magnetic energy built up. It gets stressed and contorted, and when it breaks, it can send off enormous amounts of energy out into space. It sends it back down to the sun, and therefore you can get solar flares. So solar flares are usually a result from stuff reconnecting and coming back to the sun. CMEs, coronal mass ejections, which we'll talk about more later, send energy off into space. Some stuff gets just stuck in the sun. Those are usually associated with solar flares. But we do get ejections from the sun without a solar flare. And the reason that is because some of that chromospheric material suspended in field lines, it's trapped there. Those of you that can make out this diagram, there's magnetic field lines, and these filaments sit in there kind of trapped by the field lines. Think of them as clouds, like we get our clouds here on Earth. They're cooler, denser areas of material suspended further out into the corona. How they get there, who actually knows, but they eventually form and they get trapped in these field lines. When those field lines break, you get stuff like this. That's a huge scale. Look at the curve. That's the sun. That thing was massive. Okay, that's the stuff that goes flying into space. All this plasma that doesn't belong there, hurtling off into space, sometimes at millions of miles an hour. So the direction that's going becomes very important to us. We call those giant releases of plasma and magnetic fields, because they have their own magnetic fields entwined in there, call those coronal mass ejections, CME for short. Look at these pictures. For those of you who don't know, these pictures, most of these were taken with the SOHO platform out in space at that lonely million-mile away point. Well, that black area surrounding the sun is the occulting disk. It's kind of put there in place to block the bright light from the sun so they can focus mainly on the corona. That white inner circle is the sun, the diameter of the sun. So look at the scale of these. These are gigantic, massive. And when they're on the side of the sun like that, you really get a detail of what they look like. But fortunately, when they're on the side, they're normally not of concern to us. What does it look like in motion? The time is 9:30 on this particular day, 10:30, 11:30, 12:30. That's fast. And that's a lot of stuff. There's the size of the sun. You saw how large that was. That is a lot of material going out into the medium. What does it look like when it's coming towards or away from Earth? How many of you think that looks almost kind of scary there? I do. I'll tell you what, if we see something happen on the sun and we wait, we don't always get instantaneous imagery. We have to wait for hours sometimes to get a backfill of images from the SOHO satellite, which is the one taking these nice pictures for us. So we may have something happen in the sun, we have to wait for hours and hours before we finally get images show up. And if we see anything like that, and we had a major event on the Earth-facing side of the sun, I can tell you, we're perked up. We're on alert. We're going to do everything we can to try to figure out, is that going to hit Earth? If so, when? What's the timing? So this is what they look like. Unfortunately, SOHO does not tell us. There's no Doppler shift ability on there. There's no other way of measuring, is that coming towards Earth or away? And you may think, well, come on, it's got to be obvious, isn't it? It's not. If something, a lot of times things happen in the sun which also are happening on the far side of the sun. And it's tough to figure out the timing. So we may have a flare happen on our side of the sun and may not think it's probably not strong enough to have made a CME, and something on the far side may have happened. So when we see these, we don't take it for granted that it's Earth. It may be going the other direction. And we don't want to get that wrong, either direction. We want to be right. So fortunately, we have stereo out there now, which really helps us determine that. What does this look like in motion? And if anybody who doesn't think that this looks ominous, raise your hand. I'd like to see who you are. I see nobody raising their hand. That's exactly right. That's almost kind of frightening, isn't it? That is a full halo CME. So when we see something like that, we can get a good map on it with our software that we use to help fit what's going on. It gets sent to a super cute computer over in DC, and we try to get timing on what direction it might be going, what the intensity might be, and more importantly, is it going to hit Earth, and if so, when? And that's what we try to do. And that is very difficult to do. You're talking about something 94 million miles away. You don't know exactly where the origin point was of the CME, because that's out in the corona blasting off, not from the flare that happened. That's associated with it, a result of the CME. So we don't know. We don't even know what the true direction is exactly. And when you're 94 million miles away on this tiny body of Earth and you're trying to figure out and measure this thing, it's not easy. We can be off by just a bit, and it may entirely miss us when we thought it was going to hit us. It may hit us when we thought it was going to miss us. It's not an easy business. So if you want a career that's very humbling and very difficult and very challenging because there's just not enough stuff there yet, space weather's it. We've knocked terrestrial weather out of the field. That's no longer such a challenge. This is amazingly challenging stuff. So let's watch one in motion. Solar flare, boom, stuff already happening around our ionosphere. Protons flying out, radiation storms. That's why you're seeing that snowstorm effect. This one happened to launch a CME. You probably won't even see it because the sensor gets saturated in a blizzard-like because of energetic protons smashing into it. Boom, you can kind of see the CME as it takes off, but it's flooded. This happens to satellites with energetic particles. Those that use the stars to keep their coordinates in space, those sensors get flooded and they lose track. I mean, imagine trying to focus on a star. That ain't going to work anymore, is it? So that's kind of the whole business in action. So even one more challenging element to throw in here. And for all you young folks out here that are interested in science, I have a challenge for you. Okay. Flare happens on the sun facing Earth. Automatically we're thinking, especially if it's a large scale flare, and Commander Hemmeck will get into that more in detail with our NOAA scales. But let's say we have a flare on the sun. Boom. Energetic protons, maybe. We'll see. Does it launch a CME? Yes, it did. We map it. We decide it's going to hit Earth. All right, we've made our plans. We put our watches out. We put our warnings out. We put the word out there. You're starting to hear about it in the news. Massive solar storm heading towards Earth. That could hit planet Earth and be a complete dud. Why? Who's played with magnets? Who's tried to put a positive and positive or a negative and negative magnet together? Have you ever succeeded? No, you have not, unless you tape them together somehow. It can't be done. That's the same thing with the component of the magnetic field of that ball of energy traveling towards Earth has a magnetic field. What is the orientation of that magnetic field when it impacts Earth? Makes all the difference on what kind of impact it actually has here. Earth's magnetic field is northward. When this comes from the sun, it can be any direction. We have no idea to figure that out. We don't know what it's probably going to be when it gets to Earth until it hits the A satellite. And about the time it hits the A satellite, it's going to be here in 30 to 60 minutes. So we don't know. That's the mystery of BZ. That's the component measuring that orientation of the magnetic field. So if it's southward and Earth is northward, what happens with a positive and negative magnet? That's right. Boom, they connect. They connect and we get all this stuff starts flowing down through our magnetosphere, down through the poles. You get aurora borealis, all sorts of fascinating geomagnetic storms, unfortunately for the power companies and maybe for us. But we never know what that is. So all you young folks that are still waiting to go through school and to college, interested in space, if you can solve that puzzle and we'll know what that component's going to be when it lifts off the sun, you will be famous because you will solve an enormous mystery of science. So when they finally gets here to Earth, all this CME cloud hitting our magnetosphere, traveling in at the poles, ionizing things, exciting atoms in our own ionosphere, we get these fantastic aurora borealis displays. This one on the bottom right is pretty fascinating because that's taken from a shuttle mission out in space. So there you go, northern lights. Cool stuff for astronomers and people love to look at, but not necessarily something that power companies care to hear about, or even shuttle pilots if it's going to be major. Why? Let's sum it all up on my section here by talking about one final thing. On July 23rd, and this is why this should be a reality and be something of concern to you, and I guarantee this is why FEMA, one of the reasons, tsunamis and space weather is what keeps FEMA up at night. I've heard that directly from directors out there. Why? July 23rd, 2012. There was a massive CME from the sun that took off into space. That Carrington event we talked about, remember that? 1859, the Carrington event? It's estimated that the speed of that CME to get here in 18 hours was about 2,200 or so kilometers per second. This thing traveled at over 3,000 kilometers per second. Okay? This took off, fortunately, from the far side of the sun. Stereo imagery's captured it. You can see stereo A happened to be in a position that it saw a full halo. Did stereo get hit? Yes, it did. Stereo A was in a different direction. It saw a side CME, just like we did here at Earth from SOHO. We saw it from the side right there. Fortunately, that didn't come towards Earth. What if it had? If that had happened 8 to 14 days earlier, that same CME, Earth would have been smashed by this thing. What would have happened? Massive flare on the sun. Boom, instant radio blackout, because that flare certainly had to be strong enough to reach through the strongest levels of our warning on it. Ionosphere facing the sun would have been completely ionized. Black signals would have made it through the ionosphere and bounced like they normally do. They would have been absorbed, lost. Radio blackout, boom, immediately for hours because it was such a big event. A CME took off at nearly, it's estimated, about 3,400 kilometers per second. Way faster than the Carrington event, way faster than the event of 1989. That's New York to Rome, Italy in 2 seconds. That's the speed this was hurtling through space at. There was probably an energetic proton event with that may have jumped up all the way through the radiation scales. That got here in less than 30 minutes and would have been pulverizing our outer atmosphere and swarming in through the poles. They don't reach the surface. They still get absorbed and captured out there, which is a good thing for us. But nevertheless, they would have been in there. A CME would have been crashing into planet Earth's magnetosphere and starting to swarm around in this big CME cloud in half a day. 12 hours. The Carrington event took 18 hours. I told you we have to wait for backfield imagery. Sometimes we got to wait for 6 hours or more. That's frightening to us. That's too fast. That may have gotten here without us even being able to notice that it happened yet. We may not have gotten the imagery yet to see what kind of CME took off from the sun. So that's very disconcerting. That would have done all sorts of things. That would have smashed into our magnetosphere and immediately compressed the front end of it. Just pushed it in. Some satellites that are normally inside the magnetosphere would have been suddenly outside, getting pulverized by particles they don't normally get pulverized by. It would have been pushed in. When it gets pushed in, that creates all sorts of energy. You get this extra currents flowing, these geomagnetically induced currents along power grids. Power companies would have started having problems shortly afterwards as the storm continued to develop, the geomagnetic storm. This storm, it's estimated, could have been on the order of 1,200 nanoteslas. What does that mean to you? Normal minor level storms are only 50. The Hydro-Quebec Canada storm of 1989 was about 600, getting pretty large. Now we're talking 1,200, 2 times the intensity of the one that knocked out power in Canada. That is incredible. That's what probably would have happened if that CME had come directly towards Earth. We're talking the top of our NOAA scale, which Commander Hemmeck's going to talk about. Widespread, not radio blackouts now. Those are still going on, and especially around the poles. Power blackouts. People are going to lose power, especially in the northern tier states. Europe. Southern latitude places like southern Chile or Argentina. Catastrophic event. It's estimated that if that event had hit planet Earth, we would have had $2 trillion in damages. Why? Satellite problems. The atmosphere heats up, it slows down a satellite. What happens when a satellite slows down, do you think? It lowers in its orbital altitude, and therefore they have to fire things to get it going again and find it again. Transformers would have burnt out. It would have taken years in some cases to replace those. I told you a lot of those aren't just sitting on a shelf. They got to make them. So that alone is something of major concern to our government, and that's why there's like a strategic weather plan out there now, because we were so much reliant on today's technology that space weather is really becoming more and more important. And with that, I'm going to jump into Commander Hemmeck's portion. He's going to touch briefly on the NOAA scales of the 3 things we look at, and then on our webpage, and then straight into his talk.
So I'm not going to sleep tonight. Thanks, Shawn. All right, so should I put that on too?
I don't know. It's up to you.
I think I have to for.
If I can get it off. There we go.
Was it glued on? You want to slap it on me? How's everybody doing tonight? Good. Are we hanging in there?
Here's the pointer.
All right. Okay, so you can hear me?